Welcome. I'm going to talk to you in this special video about the ellipse. This video is solely about the ellipse and I'm going to be talking to you about lots of interesting things. But before I do, let's take a look at that. I mean, that is pretty cool, okay? It gives you an idea of why ellipses are important, because when you deal with orbital paths, for example, the Earth that's orbiting around the Sun, it's an elliptical path, okay? So that alone is pretty cool. So what's coming up in my video? I'm going to be talking to you about the general equation of an ellipse, both in parametric form and in Cartesian form. I'm going to be talking to you about the shape of the ellipse, and I'm also going to be talking to you about other cool stuff such as the focus points of the ellipse and the directrices. And there's a really handy formula coming up in terms of the A, E and B, which stands for respectively the A value there, B value there, the intercepts between the X and Y axis, and E, this thing called the eccentricity. What actually is that? I'm going to be talking about those things coming right up. I hope you enjoy it. Stay tuned. Or at least hang out for as long as you possibly can. It does start to get complicated at some point. So let's talk a little bit more about the ellipse. Well, here's an ellipse, and this is the Cartesian equation. X squared over a squared plus y squared over b squared is equal to 1. It should take a moment to think about that. It's very similar to the equation of a circle centre of the origin, isn't it? If a and b were the same, then this is effectively going to be a circle, because you could bring the a squared over to the other side. X squared plus y squared equals a squared, where a would be the radius of that circle. When the two denominators here are different, then it's an ellipse. To work out whether it's an ellipse stretched out this way or this way, quite simply work out the x and y intercepts. So if I cover up that one, that means y is 0, you're going to have x squared must be equal to a squared, or x is equal to positive or negative a, hence a0, negative a0. Cover up the other one, x is 0, y squared is equal to b squared, y is positive or negative b, hence 0b, negative b. So if the value of this denominator is larger than that one, it's going to be stretched out this way. If the value of the denominator is larger, in other words, if b is greater than a, it's going to be stretched out that way. Okay? In terms of the parametric equations, here they are. X equals a cosine t, y equals b sine t. T being between 0 and 2 pi radians. You can just check that, of course. The parametric equations here, you can just make cosine t the subject, x over a. You can make sine t the subject, y over b. And then using the identity, cosine squared t plus sine squared t equals 1. If you square these together, sine squared t is that, cosine squared t is that. Then you add them together, this plus this equals 1, hence the Cartesian equation. Okay? Let's do a couple of examples, simple examples. So let's just clear that, put that over there. So one simple example, I'm going to write down an equation, 4x squared plus 9y squared equals 36. Now, you'll see this is not really in the form that we would like it. We'd rather, for an ellipse, to have it in this form here, x squared over a squared plus y squared b squared equals 1. So the thing to do is look at the number on the right hand side and divide by that number to get 1. So divide both sides by 36. Okay, so when we do that, we'll have x squared over 9 plus y squared over 4 is equal to 1. Now, for reasons that you'll see later on, okay, it's often a good idea to work out the values of a and b. So I'm going to write down a is equal to 3. Remember that a squared is the denominator here, so a squared is 9, a is equal to 3, and b is equal to 2. Now at this point, don't worry about the plus or minus, okay? I cover that in terms of a and negative a, okay? So just for the moment, go with a is 3, b is 2, don't worry about the positive or minus. So you can see on our sketch here, that will be 3, 0, negative 3, 0, and that will be 0, 2, 0, negative 2. So it looks pretty much like that. In terms of the parametric equations, that a and that b there are what we're going to have. So you have x equals 3 cosine t, and you have y is equal to 2 sine t. Okay, that's it. Rather simple example. Should we do another one? Yeah, let's do another one. So let's just get rid of that. This time we'll give you the parametric form. So x equals 3 cosine, and use theta this time, ooh, a little bit different, But traditionally we use either t or theta, okay, for these parametric equations. 5 sine theta. And what we're going to do is just draw a sketch. Can you do it without working out the Cartesian equation? Yes, you can. Because if you compare the parametric form here and these, you can write down straight away A is 3 and B is equal to 5. If you want to do the working for the Cartesian equation, it's quite simple. Remember, you just do x over 3 and then squared, so x over 3 squared, so x squared over 9, and then y over 5 squared to get sine squared theta, so that's with y squared over 25 is equal to 1. And again, you'll get A is 3, B is 5. What it tells us at this time is that this graph is going to be stretched that way. Okay, let's do a quick sketch of it here. This is not the greatest of my sketches, I have to say. Look at that, that looks awful. Absolutely terrible. Looks a little bit better. But what that means is that it's stretched vertically. Now I'm going to introduce a term for you. I'm going to introduce the term major axis. Okay? We say the major axis in this case is that one, the horizontal axis, because it's been stretched out that way. It's actually larger from left to right than it is up to down, if you don't mind me saying like that. This one we call the vertical scale, the major axis. Okay, you don't really need to know it, but sometimes these things just help. Okay, so you've got a major axis and a minor axis. The major axis is always the one where you can see the ellipse has been stretched out from a circle, and that's the minor axis. Okay, well, I'm hoping that was helpful to you. Right? Now we're going to learn a little bit more about the ellipse. There's a lot going on here, isn't there? There's a lot to take in. Yeah, but you've got to know it all. So in terms of an ellipse, we talk about focus points and directrices. You should know what they are already from your work on the parabola. But the ellipse has got 2 focus points. Here, the first one labelled S, coordinates AE0. And here the second one labelled S dash or S prime, negative AE0. So notice that they're symmetrical about the y-axis. For the directrices, you've got this one, x equals a over e, and this one, x equals negative a over e. We'll come to e in a minute. These values of a are exactly the same as the value of a there. You've already met the parametric form for an ellipse. And also, with the Cartesian form, that's the same as the value of a there. Now, what do we mean by e? Well, e is called the eccentricity. You need to know about the eccentricity for the ellipse and for other curves as well. But for the moment, we're just talking about the ellipse. The eccentricity is defined as follows. That e, we use for eccentricity, is the distance ps over the distance pm, set up as a ratio. What do we mean by ps and pm? Well, that's what the diagram is here for, to try and help you to explain what that means. We're interested in the distance of any general point on the curve. Now, for a general point in the curve, I always try and choose a point that's in the top right quadrant, the first quadrant, because then we're dealing with positive values, just keeps things nice and simple. But P could be anywhere on this ellipse, okay? So looking at a general point P on the ellipse, we look at the distance from P to the focus point here, and the distance from this point P to the directrix, okay? If you remember the focus directrix property of the parabola, okay, the property was that the 2 distances were the same. We can see on the ellipse that's not true. Okay, you can see on the ellipse the distance PM is obviously greater than the distance PS. Okay, also go to focus directrix property. However, we tend to call it the eccentricity. The eccentricity is defined as this distance divided by this distance here, and we say that the value of E is between 0 and 1. We'll get to what happens when E is greater than 1 afterwards, okay? And also what happens when E is 1. Let me just clarify this one. When E is 0 itself, you get a circle, okay? So eccentricity being 0 gives you a circle. When it's greater than 0, but still less than 1, it gives us an ellipse. Okay? And then we go to a parabola for when it is 1, then we go to a hyperbola for when E is greater than 1. Okay. Interestingly, when E tends towards infinity, you've effectively got a straight line, but that's another case. Okay. So sometimes we calculate a value of E, and if we know the value of E, then that informs us what the focus point is, and it also informs us what the directrix equation is as well. Or other way around, if you're given the coordinates of the focus points and you're given the Cartesian or parametric equations, you can use those to work out what the value of E is as well. All these things you need to know, by the way. Right, similarly, the same holds for any point P and the distance between that and the other focus point, and distance between that and the other directrix there, okay? So if I just show you, if we look at this distance, P to S dash, and the distance P to, let's call it M dash, then the same ratio holds, okay? So it doesn't matter what point you choose on your ellipse or which focus point you use. This eccentricity rule is always going to hold, okay? Now, before I move on, let me just quickly introduce these bits, because it's rather handy to have them here. You have an equation, a formula, which hopefully I'll explain in a separate piece, a formula relating B, A and E, which is a rather handy formula and one that you need to be able to know and use as well. Okay? For reasons you'll see some other stage, when A is greater than B, now remember I talked about that in terms of the major axis and which way round the ellipse is being stretched, but for the cases when A is greater than B, the formula relating A, B and E are B squared is A squared 1 minus E squared. Other way round, when you've got B is greater than A instead, so this number here is greater than that number, then you've got a different major axis, then you use this formula here. A squared is B squared 1 minus E squared. Can you see, you just switch the A and B around depending on which one is larger. But I thought I'd just put that in now because it's helpful if you're making notes on all of these different things about the ellipse. Right, I want to consider these now. Why does that formula work? Let's have a look. So what I'm going to do is, I'm just going to focus on this part of the ellipse, because to be honest, you don't really want to be looking at all the stuff that's not needed, right? Let's just look at this, right? Notice what I said there, let's focus on the ellipse. I didn't do that on purpose, trust me, but these things just slip out, okay? I've just got a habit. So I'm just going to look at that focus point there, and this directrix there, okay? And we're going to use the fact that PS over PM is equal to E to come up with this relationship between B, A and E. Now, let me just show you how this works. If it's the case that PS over PM is equal to E, we can say this is true as well. Because you can square both sides and then multiply both sides by PM squared afterwards. So you get PS squared equals E squared PM squared. So what that means is that this distance squared represents PM squared, and this distance here, PS squared, represents this bit there. All right? We just need to have an expression for each of these, and then we're done. We should have the relationship, because we can get an expression for PM squared and PS squared, all in terms of A, E and B. All right? Maybe you pause the video and have a go, see if you can do it yourself, and then just unpause it and get back to me. Otherwise, you can just stick with it, and I'm going to talk you through it. So let's look at PS first of all. To find PS, use Pythagoras' theorem. Okay? So you've got that distance there, that's just the y coordinate, so put it in there as the y squared, and then you've got this bit here, that's going to be the difference between AE and X. I'm not going to draw the right angle triangle in. At this stage, you can kind of imagine it's there. All right? I don't think I need to draw a right angle triangle now that you've got to this stage. So you've got that distance there must be AE subtract X. So you've got AE subtract X squared, or the other way around, X minus AE squared. I personally prefer it that way because when I'm expanding brackets, I genuinely prefer having X squared as being positive. So either AE minus X all squared or X minus AE squared, it's the same thing, isn't it? And when you expand the brackets, of course, that's what you're going to get. Okay, happy with that so far? In terms of PM, that's a little bit easier because it's a horizontal line, so you just need to have the difference in the X coordinates for that. So you've got here the X coordinate, A over E, and then the X coordinate there is just going to be X, hence A over E minus X squared. Okay, and then we're going to be using E squared, PM squared. Okay, and then if you expand the brackets out, you should get E squared times all of this is equal to A squared minus 2AX plus E squared X squared. I'm sure you're happy with all the algebra. All right. Then where's this going? We're going to apply what we said we're going to use. PS squared equals E squared PM squared. So let's just take a moment to consider shall we? So I can't actually fit it all on, so I'm not going to try it. What we're saying is that this there is exactly the same as this there. That's what we're saying. That line is the same as that bit there. Can you see that these two will just cancel because you're going to have negative 2ax is equal to negative 2ax. So we just want to write x squared plus a squared e squared plus y squared equals a squared plus e squared x squared, which is the next bit coming along. There we are. I can fit all of that one on nicely. And then I'm just going to tidy it up a little bit. Okay. So I'm going to get the x squareds onto one side and factorise. So if I bring that over, you'll have x squared 1 minus e squared. Keep the y squared there. And then same again with this. Put the a squared, e squared term onto that side and factorise a squared 1 minus e squared. Okay. And then, can you see what happens next? We can write down this line. Okay. If we just have both sides divided by 1 minus e squared, because that will cancel, you've got y squared over 1 minus e squared. Also divided by a squared, you'll end up with x squared over e squared plus y squared over this is equal to 1. And then the significance of that is, if we go back to the Cartesian equation, the Cartesian form, then it must be the case that b squared on the denominator there is the same as that, a squared 1 minus e squared. Hence, b squared equals a squared 1 minus e squared. Okay. That's only going to work though, let me just point this out, when e is between 0 and 1. Can you see if that's not the case? Okay. I mentioned earlier about the case when e equals 0. Can you see what happens? When e equals 0, you get a squared times 1, you get a squared and a squared, the circle. Okay, because they're both exactly the same. What about when e is greater than 1? Well, when e is greater than 1, can you see that this bit here is actually going to be negative? Because you've got 1 subtract a larger number. Then you get x squared over a squared subtract. That will be the case for the hyperbola. Okay. What about when e is 1 exactly? E equals 1, 1 subtract 1. Oh dear. Yeah. So we don't want to have e equals 1, do we? Okay, in this particular case. Right? What we do actually end up with when e equals 1 is a parabola, but the whole thing just breaks down when e equals 1 here. Right? But when e equals 1, you do actually have a parabola. So I'm hoping that explains where that comes from. Okay. What about the other case? Let's just go back to this page. What about the other case when b is greater than a? Just work through the whole thing again with b being greater than a and you get exactly the same result. Otherwise, I'm sure you'll agree, the only difference really is you're just swapping around the major axis, making it the y-axis instead. You can just be happy with swapping these two around as well. Okay. I'm hoping that made a lot of sense to you. If not, just watch the whole thing again. Well, that is it. That's all you need to know about the ellipse. Okay. I hope you found it useful. Okay. There'll be another video coming up on hyperbola. Okay. If you enjoyed this one, give the hyperbola a go. Just a warning, it is as difficult, as challenging as the ellipse. Okay. See you again. Thanks.